turned out that the numbers of all types that reached our detector, only 1/3 of them were electron neutrinos. And that indicated that 2/3 of the electron neutrinos produced in the core of the sun had changed into the other types while passing through the sun and before reaching our detector. That was not predicted in the standard model, and it also implies neutrinos have a finite mass.
Welcome to My Nuclear Life. I'm Shelly Lesher. Today it is my pleasure to be live in the studio with Nobel Laureate Art McDonald. In 2015, he shared the Nobel Prize in Physics with Takaaki Kajita. While Dr. McDonald led the SNOW lab in Canada, Dr. Kajita used the Super Kamiokande detector in a mine in Japan. Their joint citation read, "For the discovery of neutrino oscillations, which shows that neutrinos have mass." You will hear how their discovery changed the way we think about the universe. Art is at the University of Wisconsin-La Crosse as part of the Physics Department's yearly Distinguished Lecture Series, where we bring in a Nobel laureate to give a lecture and interact with our undergraduate students and the general public. It has been amazing having him here. I hope this episode gives you an idea about how much fun it has been to have him around the department. Just a note, a few hours before recording this podcast, we were joking about the differences in units between the US and Canada. This is why Art converts things from meters to miles, and in some cases, football fields. I wanted to start by asking you how nuclear physics has influenced your career.
Well, my PhD from Caltech in 1969 was a PhD in nuclear physics. I was studying, in this case, nuclear reactions that enabled us to understand the detailed properties of what are called higher isospin levels. But basically all of the work that I've done in nuclear physics, and to some degree it's true also for the Sudbury Neutrino project, is using nuclear techniques to try to understand basic laws of physics that underlie everything, including nuclei. We were studying higher isospin levels, which is a symmetry properties in nuclei, particularly in our case late nuclei, to try to understand whether the Coulomb interaction, the electromagnetic interaction that we understand very well in external situations, also works to understand what's happening inside the nucleus. And so we made a number of measurements of nuclei that look very similar, but you change the number of neutrons for the number of protons, just switch them, and you get symmetries in nuclei that way. So that was my initial work, and I was doing that in a laboratory at Caltech called the Kellogg Radiation Laboratory, which was headed by William Fowler, who developed all the theory behind, in many cases, the experiments used to understand the nuclear reactions that power the sun. So it was in that context that I was doing what amounts to symmetry measurements in nuclei, but I was also paying attention to the other things happening in the laboratory.
Did he influence, or did he put that seed in your brain about that interaction?
Well, at the time, the question of neutrinos from the sun was a very big part of discussion at the laboratory. John Bacall, who was the preeminent theorist in the calculations of how the sun burns, was a junior faculty member at Caltech. Ray Davis, who did the initial measurements of neutrinos from the sun and found that there were 3 times fewer than was predicted by John Bacall's calculations, leading to what came to be known for many years as the solar neutrino problem, used to visit in the summer. A lot of discussion going on the topic. One of my colleagues, one of my fellow graduate students, was making measurements of the nuclear energy levels of chlorine, which was the detection technique in a large tank of cleaning fluid in the Homestake mine in South Dakota. And there were a lot of discussions going on, particularly when it was found fairly quickly that this factor of 3 existed. And so then it switched into, do we have the calculations of how the sun burns wrong? A lot of work done on that through the 1970s. Ray Davis started his measurements in 1968.
I'm sorry, what's the factor of 3?
Factor of 3 is that the number of neutrinos observed were 3 times smaller than calculated. So the solar neutrino problem was a question of whether the calculations of how the sun burns, which are very important in understanding the nuclear reactions that create essentially the major elements from which we as humans are formed, carbon, nitrogen, oxygen, and lighter nuclei before hydrogen, whether those were understood, and therefore, to some degree, how we understand our origins in that sense. But they're also important because we're going to use essentially the same reactions to generate power here on Earth through fusion in what's called fusion power. And in fact, in the next few years, there will be the first demonstration reactor, tokamak reactor in France, the International Tokamak Experimental Reactor, ITER. France, United States, Japan, Canada are involved in this. What we did in measuring the neutrinos from the sun that come from these reactions, and what Ray Davis had been measuring and finding a discrepancy, the calculations that are done for how the sun burns, held in place by gravity, are very similar to the calculations for how fusion power is generated here on Earth, held in place by magnetic fields, and thereby preventing particles from touching the walls of the vessel and melting it, basically. So these were important questions, but the alternative, if it was not that the calculations of the sun were wrong, was that you had to change substantially the properties of neutrinos as expressed in the standard model for elementary particles at the most basic level. That, in fact, when we, in 1984, started the Sudbury Neutrino Observatory, those were the 2 questions on the table.
Wouldn't it be easier to believe that the calculations were wrong?
Well, certainly that's what most of the high-energy physicists and theorists who had worked out the standard model were feeling. In fact, so we performed the Sudbury Neutrino Observatory measurements and started in 1984, eventually had our definitive results in 2002, a long time later.
I was going to say, wait, 84 to 2002, that's...
Long time.
That's a career.
Well, yes, I guess you could say that. There have been many other things that many people who worked on it have been doing and that are very influential in the field. But yeah, for some it was a career. The reason I mention it is the way you asked that question. After the Sudbury Neutrino Observatory results, I have a tape of a New York TV program interviewing John Bacall and saying, how do you feel now that basically your calculations have been accepted and neutrinos do change from one type to the other, and that's why they were eluding these other experiments, and you have to change the standard model of elementary particles. And John's answer was, I'm very elated. I feel like dancing because I feel as though the DNA evidence has come in to absolve me of my crimes as viewed by certain members of the community. In other words, there was a lot of debate back and forth. But our measurements, we took advantage of some very substantial advantages we had in Canada in this international Canada, US, UK experiment. Availability of something called heavy water and the availability of a deep underground site to get away from cosmic ray background. They enabled us to do the experiment, and so we took advantage of that and spent about 20 years working on making it happen.
So I want to go back to, could you explain what the standard model is and why it's important?
Sure. So the standard model of elementary particle physics is a model that basically describes all of the data that we have from nuclear physics measurements, from cosmic ray measurements, from accelerator measurements of particles banging into other things. And it describes the basis for not only the atomic structure of matter, but deeper inside that atomic structure. I mean, what you learn in high school is that atoms are made of a nucleus with electrons going around the nucleus. The number of protons in the nucleus matches the number of electrons, and the number of electrons affects the chemical properties. We now know that inside the protons and the neutrons, which are neutral particles in the nucleus, there are quarks, as they are called. We don't know how to subdivide quarks any further. We don't know how to subdivide electrons any further. We do know that there are heavier versions of each of the types of quarks that we have, and heavier versions of the electrons as well. And then there are these other particles called neutrinos. And these neutrinos are very unusual. They have no electric charge. They only feel the weakest of the forces of nature, the weak interaction as we call it, and they don't feel the strong interaction that binds the quarks inside the protons and the protons and neutrons inside the nucleus. Having no electric charge, they don't feel the electromagnetic interaction in that way. So they're very unusual, but they happen in nuclear reactions that power the sun. There are billions of them being produced and more. There are billions of them going through us right now from the sun. But they interact so seldom that maybe once in our lifetime they will change one atom in our body into something else, and we don't even notice. So they are ideal when it comes to getting information out from the core of the sun, but they're very difficult to detect.
I was just about to mention they seem almost impossible to detect.
Well, Wolfgang Pauli, who originally proposed that they might exist back in 1930 or so, he proposed it because people observed a certain kind of radioactivity called beta decay, where an electron is emitted from a radioactive nucleus. And instead of a single energy for the electron being emitted, which is typical if you keep track of the difference in energy between the two nuclei involved in that radioactive transition, instead of a single energy, there was a continuum of energies, as though another particle was being emitted and taking away some of the energy. So the electrons had a range of energies up to a certain maximum. Pauli is quoted as saying, "I've done something terrible. I've proposed a particle that cannot be detected," referring to what came to be known as the neutrino. But they were detected. Fred Reines won a Nobel Prize for detecting them directly for the first time from a nuclear reactor. Mm-hmm. And they have a big influence, in fact, on how the universe has evolved. They have some influence on how galaxies form, for example. It turns out that something called dark matter has a greater influence, and we don't know yet what that is. But neutrinos have an effect on that, and also the solution to how they fit into this standard model and how they get a finite mass, which is implied by the fact that they change from one type to another, is something that may also solve another big puzzle for us in terms of how the universe evolved. And that is, we think that in the original Big Bang, energy was converted into equal amounts of matter and antimatter.
Okay.
Antimatter is something that is basically, everything is complete opposite from its matter-particle comparison. People are most familiar with them as positrons.
Okay.
Positrons are the antimatter particles corresponding to electrons. If a positron interacts with an electron, then they get converted into energy, which is in the form of a pair of gamma rays, which go off back to back. My master's thesis in 1965 was studying the properties of positrons in metals, basic science. But 10 years later, this property of positrons, of gamma rays going off back to back, was incorporated into something which is called positron emission tomography, PET, PET scans, which has been very, very helpful in medicine ever since, which is a fine example of how basic science eventually enables new technology. In this case, it's easy to see how positron emission tomography works. Let's suppose you want to study a tumor in someone's head, and you want to see whether the blood is flowing to it or not. You can put into the bloodstream of a patient a radioactive material that emits positrons, and those positrons will flow up the bloodstream into the head, and if you surround the person's head with detectors of these gamma rays, and you take the data from this and you match up detectors on either side of a person's head where the two gamma rays that go off back to back are detected, and draw a line between them, and you get enough of these lines by having lots of pairs of detectors, you can localize where the radioactivity is occurring, where the blood flow goes in the brain, and where it doesn't, which enables you to figure out how a tumor is. But in any case, these antimatter particles are a fundamental element in our overall understanding. But there are very few of them in the universe as we know it. We have a universe made, you and me, the table, they're all made of matter, not antimatter.
Right.
Only in radioactivity do you get the antimatter particles. So somehow back in the early universe, that antimatter that we think was generated in equal amounts with matter, and we think so because there, it's the reverse process. Energy is being converted into equal amounts of matter and antimatter. Positron emission tomography, you bring together matter and antimatter, and you get energy, the gamma rays. In the early universe, equal amounts of matter and antimatter, but all the antimatter has decayed away. And it is thought that some of the detailed properties of neutrinos that are now being studied in world-class experiments, we are looking at something called neutrinoless double beta decay in our very low radioactivity underground environment. Fermilab is attempting to study other properties of neutrinos by creating neutrinos with their accelerator beams and allowing them to shoot to an underground detector in South Dakota in the Sanford laboratory. These all will contribute to an understanding of why all that antimatter decayed away in the early universe, which is one element of our understanding of our origins going back to the Big Bang.
Do we have any idea what happened to that antimatter yet?
Yeah, there are models, but in those models, there are particular properties of neutrinos that have to exist in order for the model to work. And the experiments being done here on Earth are looking for an answer to what those properties of neutrinos are and whether they match the theory.
And we don't have a good track record with understanding neutrinos.
It's getting better. We had a poor track record for quite a while because they're so difficult to detect. But since the Super Kamiokande experiment and our experiment, for which we shared the Nobel Prize with Super Kamiokande, there have been many other measurements of further properties of neutrinos, and they are very strongly understood now.
Okay.
In terms of their own properties. But there are still some things remaining to be answered, and one of them is this symmetry property that would enable neutrinos to participate in the process of antimatter decay in the early universe. We know a number of things that are to be measured in order for the theories to then explain things. If they are measured to be zero, then maybe we have to revise the theories. But right now there's a very straightforward, well, relatively straightforward theory that if these measurements pan out, we have an understanding of why we have a matter-dominated universe.
That'd be really interesting. So you spoke about how it's hard to detect neutrinos. So the question is, how do you detect neutrinos? How did you detect neutrinos? You mentioned that being underground and having heavy water was the key.
So you should understand why it's hard to detect neutrinos.
Yes.
It's because a neutrino will only stop and do something if it hits the nucleus of an atom or the electron going around the outside, one of the electrons on the outside, head on. So for it, matter is essentially open space. It can go through the distance that light travels in a year of lead. Imagine a wall of lead equivalent to the distance that, it's 1,000,000 billion kilometers of lead. I know, translated into miles, divide by 1.6.
It's a lot of lead.
Okay. 1,000,000 billion over 1.6 miles of lead. Sorry, we scientists have a different language, right? The detection, therefore, is very difficult, but the detection is in several forms. One of them being when it hits electron, you see that electron moving in materials and producing light.
Okay.
That's what Super Kamiokande used for their detection technique. The other is it hits a nucleus, and if it's a deuterium nucleus, then there's an extra neutron in the nucleus. Heavy water is D2O, has an extra neutron in each hydrogen nucleus in H2O. Therefore, it doesn't change the number of protons and hence the number of electrons in the hydrogen. It just makes it heavier. The neutrons don't do very much except make it heavier. And so that neutron, if a type of neutrino emitted by the sun, electron neutrino, strikes it, it makes a fast-moving electron and a slow-moving proton that doesn't do much. That fast-moving electron is one of the things we observe to make essentially a cone of light. It's like a sonic boom in light. And that's a measure directly of the electron neutrinos that have survived and reached the Earth and through the Earth to our detector. The other reaction that we observe is where a neutrino comes in and it just breaks deuterium. Deuterium is just a neutron and a proton. Breaks it apart, producing a free neutron. And we had 3 different techniques for detecting those neutrons. The third technique simply being an array of neutron detectors. And that measurement then is any of the 3 types, electron neutrinos, muon neutrinos, or tau neutrinos. Any one of them can do what I just said.
Okay.
And so if we observe that, we have the sum of all neutrino types. It turned out that the numbers of all types that reached our detector, only 1/3 of them were electron neutrinos as measured by that first reaction that I mentioned with the sonic boom in light. And that indicated that 2/3 of the electron neutrinos produced in the core of the sun had changed into the other types while passing through the sun and before reaching our detector. That was not predicted in the standard model, and it also implies neutrinos have a finite mass.
So does that account for the factor of 3?
Yes. What we saw was very much in keeping with what Ray Davis saw. And in fact, 2 Nobel Prizes were awarded. One to Ray Davis for being a pioneer in developing techniques for doing astrophysics underground, and one to us for actually making the measurement that understood that neutrinos do clearly change from one type to the other, affecting the laws of physics at a very basic level.
Okay, that's really cool. But to detect the neutrino, you're not actually detecting the neutrino, you're detecting the reaction that the neutrino
We're detecting
creates.
the light produced ultimately in the original reaction where it strikes a neutron and produces a fast-moving electron. And light production in 2 different techniques we used for studying the second reaction, and finally direct detection of the neutron in neutron detectors for the second reaction.
Why do you have to be 2 kilometers divided by 1.6 miles?
So it's actually about 1.4 miles, something like that, underground. The reason is that the cosmic rays that are bombarding our atmosphere, that create the northern lights, for example, having our atmosphere glow from the northern lights, those cosmic rays, if they were striking our detector on the surface, if we put it on the surface, we would have it glowing like the Northern Lights. And by going 2 kilometers underground, we didn't affect the neutrinos at all. They passed through virtually anything. But we reduced the cosmic rays by a factor of over 1 million. And so we were able to observe by doing that and by also eliminating any local radioactivity. The materials in our detector were very carefully selected to be low in radioactivity. Everybody took a shower and wore lint-free clothing, and we were able to build this 10-story building under conditions that are cleaner than a hospital operating room throughout the whole process of the construction. That enabled us to have very low bursts of light in our detector from anything other than neutrinos. So we actually only observed 1 neutrino from the sun an hour, and we could get rid of everything else. In the middle of the detector, in the middle of the heavy water, we had 1 radioactive decay of uranium and thorium, which are the main radioactive elements you'd find in water. 1 radioactive decay per day per ton of water, which is 1 billion times purer than tap water. So this was really pure stuff.
Yeah, you didn't have a problem with the decay of like the rock and stuff around you?
We did, but we designed the detector in such a way that in the central region where the heavy water was, and which was surrounded by light sensors, 10,000 of them, each one of them about 8 inches in diameter, so a very, very big array of light sensors. Someone calculated it would be capable of detecting a candle on the moon in terms of its sensitivity. Of course, on a very dark night, but anyway. That was in the middle, but it was surrounded by other ordinary water that had been highly purified, so it didn't produce any radioactivity. And it created about 4 meters of water that any radioactivity from the rock, in this case gamma rays from the rock, had to traverse before they reached our detector, and basically it just cut them off. So we weren't affected by those.
This sounds like a big engineering project for the 80s. Well, for now, but how did you convince funding agencies to give you money for such a big project?
Well, back in the day, this was a very major project, particularly for Canada. It was a total, in terms of capital cost, at the time, it was roughly $50 million from Canada and $25 million from the U.S. and 5 to 10 from the United Kingdom. And so there was a significant U.S. component in the project as well. We had to pass all the standard peer review processes that are typical of trying to understand whether this was a legitimate scientific effort, whether it would be worthwhile, and whether we had a reasonable chance of doing it. We passed all of those, and we still had a problem in Canada that it was more money than was typically available in the budgets for basic science, or at least science in this area. But there were lots of local politicians who could see the economic benefits of having such a major project. They were very much on our side. It took a lot of talking to politicians and talking to funding agencies and saying, maybe there should be an exception, that this is something that could really do something very significant, which turned out to be the case. And it wasn't so much me in Canada. I was a professor at Princeton at the time a lot of this work was being done. In Canada, it was people like George Ewan and Walter Davidson, to name a couple of names, who were spending a lot of time trying to not only lead the project in terms of developing the scientific case, which we did in parallel, but also talking to politicians. And there's also a very central figure, Herb Chen from the University of California at Irvine, who originally had the audacity to say, do you think we could borrow 4,000 tons of heavy water? I don't think he realized at the time he was asking to borrow $1.2 billion worth of heavy water.
Who do you borrow heavy water from?
The Canadian style of nuclear reactor uses heavy water as what's called a moderator.
The CANDU reactor.
Canadian deuterium uranium reactor. The way a nuclear reactor works is uranium nucleus fissions and puts out several neutrons in the process. In order for the chain reaction to be maintained, those neutrons have to be slowed down by striking something light, gliding with something light. Most reactors, the U.S. style, use light water and it's hydrogen that collides with. However, if you use deuterium, then it absorbs very few neutrons because it already has done its main job of absorbing the first neutron. Turns out that if you use deuterium oxide or heavy water as a moderator, you don't have to enrich the uranium in order to run the reactor. You can run it with uranium ore that comes straight out of the ground. And Canada, that wasn't in the business of enriching uranium for any other purpose, such as bombs, decided that it would develop a reactor that didn't require it to enrich uranium. And that's how the use of heavy water ended up being a significant thing in Canada. And they had 4,000 to 5,000 tons in reserve for the reactors they were proposing to build. And it turned out that Herb Chen, who unfortunately passed away about 3 years later from a leukemia in his 40s, proposed this, and the answer that came back was not 1.2 billion, but maybe 300 billion. And so we got 1,000 tons on loan for $1. Pretty good leverage.
That's a good deal, yeah.
Except we had to pay $1.5 million in insurance, essentially, when we were actually using it. But that's still a pretty good deal.
Did you have to pay for losses when you returned it?
We didn't lose much. Very, very little. We measured it to 0.1% accuracy. We even collected the stuff that evaporated.
It's pretty good. Was there ever a point when you were doing this that you thought it wasn't going to work?
Yeah, there were very difficult points in the experiment. There was one in particular, which was solved by one of my collaborators. As I say, if you want to do well in science, pick good collaborators and treat them nicely. I mean, I got a Nobel Prize, but it's really because of work that was done by 200 very talented people. Mm-hmm. So in this case, we started to turn on the detector, and we found that as we raised the water level, the electrical connections to the light sensors, which had a couple of thousand volts on them, started arcing, breaking down. Oof. And these connectors were underwater. We had tested these connectors substantially. We tested them for 4 or 5 years underwater, and also we were doing something else. We were pumping the oxygen and other gas. Particularly, we were interested in radon gas that gets dissolved in the water because radon is radioactive. And we were pumping that out. Turned out that we were pumping a lot better when we had the full apparatus in place in the full detector by a factor of 3 or 4 than we were able to do with our test apparatus. And that was the critical region in which electrical breakdown happens in these connectors. And so one of my colleagues, David Sinclair, who was responsible for that process of pumping things out and also other things associated with the water systems, recognized that even though these are underwater, you're still pumping them out if you take the gas out of the water. It's just as though you had them in a bell jar and you were pumping them down in a vacuum. Most of us don't really realize.
Yeah, I wouldn't have
degassing the
that,
water. Yeah. It's simply a question of equalizing the partial pressures across, in this case, the membranes that were sealing the connectors. We were doing a lot of tests. We had another group in the project that were designing how to buy new connectors, which would have been a really major and very expensive task because we maybe couldn't get around it. But Dave recognized this. We did some tests, and sure enough, it fit all of the data we were observing. But in addition to that, there was another situation where we were using nitrogen that comes from the boil-off of liquid nitrogen and has very low radon in it because all the radon stays condensed in the liquid because it gets frozen in the liquid. And so there was a technique whereby the same membranes we were using to take the gas out by passing the gas through these tubes with membranes could be used to put nitrogen back in simply by flowing nitrogen on the outside of the membrane. And so within 3 weeks, we had nitrogen saturating the water instead of vacuum, and still had no radon in there because the nitrogen had no radon. And so within 3 weeks, the detector was working fine and there were no breakdowns. So, and we then ran for 10 years with we had 10,000 sensors. So far, I think about 700 of them, maybe 800, had those problems. That's all in 10 years of operation. And since then, those have been repaired. So we have fewer than a couple of hundred of the 10,000 sensors that are not working now. And it's now, since we started installing them, that was the mid-90s, and we're still running the detector for another experiment in 2022. So over 25 years. So these are quite remarkable sensors.
That's good engineering.
Very good. Produced by Hamamatsu in Japan, by the way.
What led you to conclude you needed such a large detector and this massive amount of heavy water? What was the step leading up to that? So I'm guessing you were intrigued by the neutrino problem.
Well, that's where all the research that has gone into understanding how the nucleus works, nuclear theory, really came to the fore because we went to nuclear theorists and we asked for neutrinos of the energies that are produced in the sun. If they're electron neutrinos, how many times will they interact with a deuterium nucleus to produce this sonic boom electron that I was talking about? They were able to calculate that very accurately because they understood very well from all of other measurements that have been made of deuterium and hydrogen and from sophisticated nuclear theories that understand the deuterium nucleus very accurately, and from a knowledge of the weak interaction, which, as I said earlier, is the only thing that neutrinos do, is interact by the weak interaction. They were able to calculate that to better than about 5%. But we were presented with, in our experiment, taking the ratio of that reaction to the reaction that all neutrino types would produce when they break apart the deuterium. And they could calculate that as well. In fact, there were some uncertainties, but in the ratio, they were certain from other tests that are done and so on, that the ratio was accurate to about 2%. So we really had, thanks to the nuclear theorists, a very solid basis for not only knowing that we would only see a neutron an hour if we had 1,000 tons and could get rid of the radioactivity, which was the big question, but also when we made the measurements, we had very little uncertainty in what the probability is for the neutrino to interact in the material we were using to detect it. So that's where you work hard on basic nuclear theory, and it's of value in many different ways.
I had a picture of everyone after you turned on the detectors waiting for an hour to see a neutrino hit one of the detectors.
Yes, although seeing a neutrino in the first instance it was difficult to be sure because you needed to do much more sophisticated analysis. You had to perform measurements that removed anything that couldn't possibly be a neutrino but was present because of small electrical pulses from the detector itself and other background, which if you studied it carefully and determined where in the detector it it occurred, the outer regions had more radioactive background than the inner regions, so you had to do sophisticated measurements. But these cosmic rays that made their way through, which were, by the time we did all this, well, the depth of the experiment meant that we were only getting a few of those an hour as well, maybe 10 an hour, something like that, or less. But they were very distinctive because they're very high energy, and they produce very obvious signals. But at 10 an hour and very obvious signals, that's what everybody gathered around. We turned it on, everybody gathered around the computer screen and said, hey, we just saw a cosmic ray, the detector's working.
That must have been a really good feeling.
Oh, it was wonderful. It was a wonderful feeling, particularly because we had been plagued with these problems just a short while before, and everybody was worried about whether or not the detector was going to work at all. So, double-barreled good feeling.
Yeah. How many days did you take data before you actually stopped it and had people sort through it and see if you could find a neutrino? I'm guessing that you had multiple people working on it at the same time to verify results.
Yeah, one of the advantages of the internet is that people from all over the world can work together on things. I don't know if people realize that WWW was actually invented by a particle physicist at CERN, Tim Berners-Lee, in order that particle physicists could communicate with each other.
It wasn't Al Gore?
Who?
Oh, Al Gore claimed he...
I know.
Oh.
No, it wasn't Al Gore.
Okay, just checking.
Tim Berners-Lee is well known as being the person who developed this, and some days you wonder whether this was a good thing or not. But anyway, I mean, there was a lot of communication. We as particle physicists were using the internet extensively, mostly for email at this point, and we would exchange papers and talk about them over the telephone. But being able to have a whiteboard, which is what WWW gives you, you could even draw on it while you're talking. That was what Tim Berners-Lee contributed. And so we had people all over the world working on this, but we were worried, and this happens a lot in particle physics experiments and nuclear physics experiments. There's no only difference between them. The techniques are very similar. It's just a question of whether you're studying things that get down to the particle level, in other words, way inside the nucleus, or whether you're studying things that relate more to the nucleus itself. We had various techniques for blinding ourselves to the right answer so that people who were doing the analysis couldn't be led by the nose toward their bias, toward the answer they think is the possible answer. And one of the more sophisticated ways of doing it was to add in data for that second reaction I referred to that was false.
Okay.
And only a couple of people in the collaboration, neither of them me, they knew what the key process was to remove the extra data and get the final answer. So we really did have a eureka moment in which everybody around the world at the same time had the false data removed, and we knew what the answer was. And so from that point of view, it was collaborative internationally and a eureka moment together.
I think that's one of the great things about particle physics, especially experiment, is what a worldwide collaboration it is.
Absolutely. I'm working on an experiment now, which is to detect dark matter. They're particles that behave like neutrinos. They are very penetrating, probably more penetrating than neutrinos. We know that there are a lot of them there. We know that in our galaxy, there's 5 times as much mass in between the stars in the dark sky as there is in the glowing stars themselves, because, well, when you look out at the Milky Way, which is our galaxy, our collection of stars, it looks like a band of stars across the sky, because it's a pancake. You're looking along the edge of the pancake through all those stars. If you turn it around and look at it sideways, it looks more like a cinnamon roll. And the outer branches of that cinnamon roll are going so fast that the gravity to pull them in to keep them going in that spiral they're in needs 5 times as much mass as you see in the glowing stars. And so it's in the dark sky in between. So we're looking for dark matter in a number of experiments in our underground laboratory that I mentioned, which is 2 kilometers divided by 1.6 in miles underground. In other words, mile and a quarter underground, or 20 football fields underground. I'm told that's what you're supposed to say here in Wisconsin if you want people to understand. So it turns out that that collaboration I'm working on right now has 450 scientists.
Wow.
15 countries, and 90 different academic institutions involved in it.
Wow.
So that's not double negative. That's not untypical. That's typical of such collaborations.
I like asking Nobel laureates this question, which is, what is an opportunity that winning the Nobel Prize has given you or has afforded you that you don't think you would have had before winning the prize?
Well, of course, there's a lot of fun things.
Like what?
I got to be Geek of the Week on the Big Bang Theory TV show.
Oh, yeah? You're on an episode?
I was not in the episode, but the technical advisor for Big Bang Theory was a student of ours at Princeton.
Okay.
So after the Nobel Prize, he said, how would you like to come and be Geek of the Week? And the Geek of the Week gets to hang out with the writers and the producer and so on. And I didn't end up doing anything, but it was great fun. I don't know if people know that it's filmed in front of a studio audience, 100 people probably. Mm-hmm. If they don't get a laugh, then they rewrite it and refilm it on the spot.
Okay.
It's a very active writers group and so on, and it was great fun observing it. The technical advisor, I think, did a very good job. If you look at the equations on the board, they are accurate. One equation that was up there at one point was neutrinos interacting with deuterium.
In honor of the Geek of the Week, I'm sure.
Well, in honor of the Nobel Prize, I think, when that happened. That was great fun. But otherwise, I mean, I was asked to participate in a review of the funding systems in Canada, the various granting councils, as they're called in Canada. So I worked with a very good group of people, about 9 people, and we came up with a very detailed set of recommendations after surveying the population and having meetings across the country. We made 35 recommendations, and I would say 25 of them have been implemented.
Wow.
And they were significant in terms of improving the way in which funding is allocated in Canada. So, you serve on lots of committees. Mm-hmm. It's nice to see one that actually has some impact. So I consider that valuable. And I think probably the prominence of the Nobel Prize is the thing that got me on that committee.
So is there anything that we haven't talked about that you'd like to mention to my listeners?
Well, one thing to emphasize is that science is fun.
It is fun.
I mean, nuclear physics is fun. That's what your podcast is about.
Well, but I will say science is fun. I mean, I do nuclear, but I recognize that all science is fun.
Willie Fowler, who was the head of the laboratory where I was a grad student at Caltech, he was a fun guy. The seminars at the Kellogg Radiation Lab were at 7:30 p.m. on a Friday evening, followed by a party at one of the professors' homes.
Oh.
Complete with the Kellogg Band, which consisted of one of the professors on the piano and about 5 other students who played trumpet and guitar and a variety of other things. It was just everybody knew each other, and we're having fun here. We're doing significant things, and we're having fun. That's my experience. If you work with colleagues that you get to know and enjoy working with, you get to be very creative. You get to do significant things in terms of understanding how the world works. When I had to write up the words for the lecture I gave at the time of the award of the Nobel Prize, I looked up Willie Fowler's lecture from 20 years before when he received the prize for having worked out how the nuclear reactions power the sun. At the top there was a motto, which was ad astra, to the stars, per ardua, with hard work, et ludum, and fun. to the stars with hard work and fun. And that's basically the way he lived his life, the way people who worked with him enjoyed lots of discussions and arguments about, I'm right, no, you're right, and so on. But enjoyable discussions where you're trying to convince somebody else of what's correct on the basis of scientific facts. So it's been a fun career. I made lots of friends and had some fun experiences as well.
Great. Well, thank you so much.
Thank you.
Thank you for listening, and a very special thanks to Art McDonald. He is actually the 20th laureate we have brought on campus, and I'm so grateful he decided to sit down for this podcast. I really hope Art and all the laureates that we've had over the years know how much it means to the students to have this experience. They frequently comment that it is one of the best things about coming to our university. Please leave us a rating or a review to help us gain some exposure. Visit us at mynuclearlife.com for more information about our podcast and to find out how to support us or sign up for bonus content. Until next time, I'm Shelly Lesher, and this has been My Nuclear Life.